we should be in the note packet again, but we're probably on page past that one. We're on, yep, on, no. No, keep going once. Yeah. All right, well, anyways, we'll figure it out where we're at when we get there. So, today we're going to talk about cars. Okay? And so we put a picture up of all of our first cars. So, Mrs. Hill had a sweet cherry red Pinto. Now, if anybody know anything about the old 70s Pintos, is that they were literally rolling death traps. Okay? Because the gas tank was right in front of that bumper. And so if it got rear-ended, it punctured the gas tank and the car exploded. That's why they stopped making the Pinto. Luckily, Kay Hill made it through. Okay? Birthday girl. This was Schmelling's Beauty. I'm guessing that is a Sebring? I think that's a Sebring. I don't know. Mine, a 1980 forest green. That one's lime green, but mine was forest green, 4-door Volkswagen Rabbit. 4 on the floor, 0 air conditioning. Yeah. My father was too cheap to buy air conditioning back in the day. We're not going to need it. Then what do we do the first year that we own the car? We take the car to Nashville. Okay? What's the average temperature of Nashville in the middle of summer? Hot. 101 degrees, no air conditioning in the car. Got to roll the windows up when you're rolling down the highway because it's too loud for mom and dad to hear anything. So, baked that trip. Huh? All right. Okay. So we're going to talk exponential modeling today. Okay. So warm up with these two things. So you're in your own notes today. We are not in the note packet. I will tell you, especially because some of you are going to be gone tomorrow, I will tell you that this weekend, while you're doing these two problems in your own notes, this weekend you will have a flipped video, so a video to watch and take notes on. The notes that you take on that video will be in your note packet from yesterday. Okay, but you have that video to watch this weekend. So give you a couple of minutes to graph these two and labeling at least 2 key points. All right, so let's see. If I plug in 0, do I want to plug in 0 here for x? I want to plug in -4, right? Okay. So I'm thinking in my brain, I want to put in -4 because that makes my exponent be 0, which makes this then go through the point -4, 2. Okay. Then, what?
Please.
If I plug in -4 for x, -4 plus 4 is 0. 3 to the 0 power is 1, times 2 is 2. Okay. And then I would plug in -3. -3 would get me 6. Agree with those 2 key points. Okay. So if that is the case, then let's see. 0 before way up. So it's kind of like that. I have a horizontal asymptote. I kind of told my classes yesterday about that, where if it's on the axes, kind of just make your dashes through it, and then you can actually see it. Good to go on that one. Love it. All right. Before I even start this one, where is my horizontal asymptote?
-2.
-2 is a number. Y equals -2 is a horizontal asymptote. Okay. So we're there. If I plug in 0, right? 0 would be a good key one to do. If I plug in 0, what's my output value? -1. Yep. Because if I plug in 0, e to the 0 is 1, minus 2 is -1. You want to plug in +1 or -1? -1 would be the easier one to choose. If I plug in -1, now I've got E. E is approximately 2.7-ish. 2.7 minus 2 is 0.7-ish. So this one would come from on high and down. Yes? Good stuff. Okay? Okay? So today we're going to talk about some modeling and changing things with a percentage. Okay? So suppose you rake your yard. It's that time of the year when leaves are starting to change. I can tell by looking out the window and I see a couple of trees that are changing. Before you get the rake hung up in your garage, there are 50 leaves on the ground already. Or nothing makes me madder than when I rake the leaves and then all of a sudden more leaves fall. Okay? The number of leaves continues to increase by 8% every hour. Find the number of leaves on the ground 12 hours after you have finished raking. Okay? So my question to you is, so when we started, we have 0 time, right? We just got done. We turn around, and there's 50 leaves on the ground. Right? Okay? Now, after 1 hour, how many leaves will be on the ground? After 1 hour is my question. You tell me how many leaves are on the ground. And we can let's round to 1 decimal point because we'll fix that in post. How many leaves we got on the ground after 1 hour? If it's going up by 8% every hour. How many leaves? How many leaves? What do you got, Cole? 54. I got 54 leaves on the ground. Cole, can I ask you a personal type question? How'd you get that? 1.8 or 1.08? 1.08. Yep, that's one way to do it, okay? Another way to do it is we could have multiplied 50 by 0.08, gotten 4, and then had to add 50 to it. Okay? Those are the 2 most common ways. We get 54 leaves on the ground. Follow-up question to that one. How many leaves are on the ground 2 hours after? $58? Do we agree with 58 exactly? Okay. That's why we're going to round to 1 decimal point, just because I wanted to, yep, Okay. So what did you get? 58.3? Now, out of curiosity, could we have 0.3 of a leaf? I mean, we could, right? There can be partial leaves. But I would agree with Cole saying we should really round this to 58. Okay? Because it's you either have one leaf on the ground or you don't, when I'm raking leaves, I don't see 0.3 of a leaf and think I've made a lot of progress. You know what I mean? Okay? I see 50, and a whole extra one. Or round it to 59 would be a really good way to do that one, right? Okay? All right? Fantastic. Let's go. So this was, we did 54 times 1.08, right? Right? Well, 54 was 50 times 1.08, and then we multiplied that by another 1.08. Okay? 3 hours after raking. How many leaves on the ground now? Three hours after. Anyone? 62.6? I got 62.9856. Yeah. But we'll round that. We'll call that 63.0 because we said we were rounding to the tens. Okay? All right? With that, then, do you see a pattern going on here? You see a pattern going on here? Yeah, yeah, okay. So this number here, let's call this number n, for whatever number we want it to be. What is the corresponding number of leaves? How am I going to figure out the corresponding number of leaves? What's it going to start with? 50 times what? 1.08 to the power of n. Yep. Okay. So now, if I ask the question, how many leaves are on the ground 12 hours after I finished raking, I don't have to do for 4, for 5, for 6, for 7, for 8. I can go right to the fact that 50 times 1.08 raised to the 12th power is 125.9 leaves. Okay. Knowing what you know from yesterday, what kind of an exponential function is this? Growth or decay? The growth function, which makes sense because more leaves are falling, that means the pile's growing, that means we got to rake again, that means, mass hysteria. Okay. So that is one way to do that. Okay? Now, if a population P is changing at a constant percentage R each year, then we have this formula. The population can be a population of anything. In this case, it could be leaves. We could be talking about spores in a petri dish. We could be talking about people in a town. We could be talking about the amount of money in your bank account. We could be talking about, the value of a car. We'll talk about that later. All those, doesn't matter what our population is, but the number of what we have is based off of the number that we started at and the rate of growth or of decay. Okay? So we're adding that rate if we're growing, because then our B value from yesterday will be bigger than 1. We're subtracting that rate if we are decaying, because then our B value would be less than decaying. Okay? Don't believe. Check to make sure there wasn't anything down there. I didn't think that there was. Okay? So determine the exponential function with an initial value of 12 and increasing at a constant rate of 3.5% per year. Okay? Well, our function once again was P of t is equal to P sub 0 times 1 plus or minus r to the t power. Okay? What is my initial value? 12. 12 is my initial value. P of t equals 12. Times 3.5% is a percent. I need it as a decimal. So 0.035. Okay, right? Are we increasing or are we decreasing?
Increase.
Increasing, so that means we're going to go 1 plus r. So then this would be 1.035 to the t power. Not gonna lie to you. My favorite example is example 3. Oops. Move back. Move back. That.
Does it involve an exploding car?
Yep.
Woo!
Huh? All right. So that is because we only asked to find the function. Okay. All right. Here we go. So you purchased a 1979 Ford Pinto back in 1985. It was valued at $1,800. It was a classic Ford Pinto. Okay? White with red striping, Starsky and Hutch style. And Starsky and Hutch didn't have a Pinto, but they had that racing stripe down the side. And sport rims. It was all the talk of Greenway High School in North Duluth, Minnesota. Hard to believe, but somehow this hot rod actually lost value at the rate of 7% each year. What I would like you to do is I would like you to find me the exponential function that describes the value of this classic piece of steel in a function of t years since 1985. Then I want you to use your function to find me the value of this street rocket in 1990. Go. Okay. Find the function, find the value in 1990. I'm not going to say that that is now the lovely and talented, wonderful Mrs. Hill, because I'm not going to say that. So we're losing 7%, so then that would be 0.93 to the t power. Do we agree with the function that I have written? Okay, it's got to be less than 1 because we're losing value, right? Now, here's the kicker. What t value do I plug in?
5.
5. Okay. Why 5?
Because it's been 5 years since 1985.
Yep, because this was T years since 1985. Classic mistake there is somebody puts in 1990. But that's not, we're looking for the value of 5 there. So I'm looking for P of 5, and P of 5 would be 100.93. I get $1,252.24. Agree? Good times. Yeah. Suppose the population of San Jose is following an exponential growth pattern. In 1990, the population of San Jose was approximately 782,000. In 2000, it grew to approximately 895,000 people. Let's create 2 ordered pairs from that given information. You tell me what ordered pairs we could come up with based off of the wordage in number 1. Two ordered pairs. That we could come up with based off of, in 1990 it was 782,000. In 2000 it was 895,000. 2 ordered pairs. 2 points on my graph. 2 points in my function. Anyone? Bueller. You know what it is called? Okay.
What's the movie again?
Ferris Bueller's Day Off. Anybody got? Give me one ordered pair. You give me one, I'll give you the other one. What do you got? How about instead of 782,000, we just go 782? Would that work? Makes our numbers a little smaller, right? Okay. I like 0 and 782. Now, if that is the case, okay, X is, or T, excuse me, T is in what? What would the condition be on T?
10.
No. It'd be years, yes. After 1901? After 1990. Yep. So my T here is going to be in years after 1990. So knowing that, 2000 is how many years after 1990? 10. So this one is going to be 10 there, not 2000. If I put 2000 there, that would be the year 3,990. Okay? P, my population, is in thousands. So the P value in 2000 would be how much? P value here would be, for 10, for a corresponding T value of 10, P would be 895. Okay? Now, we're going to use that data to come up with a model of in the a times b to the t power, right? So we want y equals a times b to the t power. Okay? Do we know what our a value is? Yes or no? A value. What is it? 782. A value is where we have our y-intercept. Okay? So 782 is A. Okay? Now, what we can do is we can use our other point, and we can say 895 is equal to 782 times b to the 10th power. Because that represents my point 10, comma, 895. What I would like you to do now is, utilizing a calculator of some form, is find me my b value, and we will round to 4 decimal places. Find me b to 4 decimal places, please. Talk to me. How do we go about finding b? First step. If I want to find b, if I want to solve for b, first step. No. Divide by 782 because it's being multiplied. Okay? So I've got to divide both sides by 782. That gives me 895 divided by 782, and I'm just going to leave it like that for right now. Equals b to the 10th power. I want to solve for b. What do I do next? 10th root it, okay? Or take it to the 1/10th power. One of those two things. When you do that, you should get b as 1.0136, because I said we were going to round to 4 decimal places. Okay? So my function, p of t, is 782 times the quantity 1.0136 to the t power. Questions, comments, concerns, clarifications? Okay. Whoa, what happened there? There we went there. Nothing else down there. I don't know why it's jumping. Okay. Okay. According to the model, what would the approximate population be in the year 2005? So what t value would be 2005? T value in 2005 is 15. So we're looking for p of 15. Find me p of 15. Remembering that the answer you get is in thousands. I get 957,483 people living in San Jose. Yours might be a little different on the tail end, on the last couple of digits. I used my exact B value. I didn't round it. Had I rounded it, it would have been 782 times 1.0136 raised to the 15th power. I would have gotten 957,648 there for that. Okay. Sketch the graph, label my axes with words. Yes, we're going to start here. We're going to go up like that. It's not going to be a very steep growth, but it's going to have some growth. We're going to label my axes in words. Well, then this is going to be population in thousands. This is going to be time since 1990 would be that. When it says label it in words, you have to label it in words. So then you can come through and you can say, all right, here was 0, here was 15. This is the point 0, 782. This is the point 15, 957.483. Ooh, here's a good one. Assuming the population continues to grow accordingly to this model, in approximately what year would the population surpass 1 million people? In order to do this one, we have to solve this one graphically. So you will need to open up a graphing page on your calculator. So we'll need to add the graph. And in function number 1, we're going to go with our exponential growth function, 782. Now you can go times, you can go parentheses, I don't care what you do, times 1.0136, and we're going to raise that not to t because our function is based off of x, so we're going to raise that to the x power. When you hit enter, you will not see the graph because we have to adjust our window. What do you feel would be some good window units for this one?
1,000.
For which one?
For minimum. For maximum, it would be 10,000.
For which one?
X.
For x, do we agree with 1,000 and 10,000 for x? Yes or no? I'm going with a hard no on that because I'm not asking what the population of San Jose is in 2990. That would be 1,000 in x. Because x is time. Remember, we described x as time on our graph.
Okay, then it'd be more like 20.
Okay, so we want to go from 0 to 20. Okay, I'm okay with that. We'll try 20 here as a maximum. Come on. Menu, window settings. 20, tab, 5, tab. Y's. What do we want to go with Y's now? What do we need to at least get up to on our graph? Exactly. What do we need to at least get up to on our graph? If we got to get to 1 million people, we got to at least get up to 1,000, right? Okay? So let's go from negative 100 to, I'm going to go to 1,200. And I'm going to go by 100s. Okay? So there's that one. Now, what's our second function that we're going to put in? What would a million be on our graph? Not 100. Be 1,000. A million is 1,000 thousandths. So I'm going to hit tab, and I'm going to put in 1,000. And what am I going to be looking for? I'm going to look for that intersection. What is that intersection going to tell me? What does that intersection tell me? What does it tell me? What are we trying to find? Okay, so when does the population hit 1 million people? So what year does the population hit 1 million people? 2008. A little bit after the start of 2008, right? So we're talking maybe February-ish of 2008. Because it's 18 years since 1990. Okay? So I would say that this population hits 1 million somewhere in February or March of 2008.